All right, we are going to talk about the basics of probability. So, outcomes are the most basic possible result of observations or experiments. For example, if you toss two coins, one possible outcome is going to be heads or tails. So that's the H. So there's a head, got President Lincoln there, and we've got a tail. Now, some of the coins have a different look on the back, but it's still a tail. If it doesn't have the head of the president on there, then it's going to be the tail. Okay? So heads and tails. And we're going to write them as H and T. So it can be heads, tails, and another possible outcome is tails, head. So this is not the same as this. Now let's flip them because that way the backs look the same. All right, trying to get the heads right side up there. So the outcome of, hopefully it's not too much glare, of heads, tails. Let me turn on the light just a little bit. Maybe that will help. I'm trying to see what you can see there. Making sure you can kind of see. All right. So here's the head, here's the tail. That's not the same thing as tail and then head. Those are two different outcomes because you get the head first and then the tail, or you get the tail first and then the head. Okay, so it does matter. All right, so an event is a collection of more or one or more outcomes that share a property of interest. For example, if you toss two coins and count the number of heads, the outcomes head-tail and tail-head both represent the same event of getting one head and one tail. So they represent the same type of event, but they're actually going to be slightly different because you did one first. All right, so the figure shows that there are 4 different ways the coins could fall. We could get 2 heads, or 0 heads, and get 2 tails, no heads. We can get 1 head with a tail and then a head, or get 1 head with a head and then a tail, or we can get 2 heads. So there's 4 different ways when we flip 2 coins that we can get, because they are the same event in the fact that you get 1 head each time with the tail and the head, but the order does make a difference. All right, and this just kind of explains, like for you get 2 tails, you get a tail head, a head tail, and then you get a head head. Okay? All right. So when we consider the possible outcomes, the order does matter. Like I've said, I'm going to repeat it several times because it's really important you understand that. So tail-head is different from head-tail. There are 4 possible outcomes for the heads represent only 3 different events. So when we're looking at this, we have 4 outcomes but only 3 events. The outcomes were the 2 tails, the tail-head, the head-tail, and 2 heads. But the event is going to be 0 heads, 1 head, or 2 heads. So there are some different differences in the outcome versus the type of event. All right, so expressing probability, when the probability of event expressed is going to be like the P of event, or whatever that is, like probability of heads or probability of tails, as so far what we've looked at. It's always going to be somewhere between 0 and 1, and including 0. It does include, that's what the inclusive means, between 0 and 1. So a probability of 0 means that the event is impossible, never going to happen. And a probability of 1 means that it's very certain. So in the middle, you'll have like a 50-50 chance, and at the impossible side, you'll have it unlikely, and at the certain, at the 1, you're going to have it as likely to occur. So using the letter P to represent probability, we express the probability of heads and tails of a single fair coin as the probability of H would be 1 out of 2. Now, why is it 1 out of 2? Well, there are 2 sides to our coin, right? We have a head and we have a tail. So the chance of it coming up heads is going to be 1 out of 2 possibilities when we flip a coin. So it's 1 out of 2. that can reduce down to, or simplify to, or because it doesn't really simplify, but change to 0.5 as well. The probability of getting ahead when there are two sides to the coin is also going to get you 1 out of 2. Now with rounding, if possible, express a probability as an exact fraction or decimal. Otherwise, round the result usually to 3 significant digits. So significant digits are digits other than 0. So we're going to get till we get the first significant, and then we'll do 3 of those. So that's typically how you're going to do probability. Once I get past the zeros, I got a 4, I'm going to do 2 more digits after that. There are 3 approaches to finding probability. There's a theoretical approach. It's based on the assumption that all outcomes are equally likely. It's determined by dividing the number of ways an event can occur by the total number of possible outcomes. The relative frequency probability is based on observations or experiments. It's the relative frequency of the event of interest that has been observed many times. And then the last one is a subjective probability. It's going to be an estimate based on experience or intuition. So let's look at some theoretical examples. If we consider flipping the coin, because there's 2 equally likely outcomes like we talked about, the theoretical probability for each outcome is 1 out of those 2 possible equally likely outcomes. If we consider rolling a single die, because there are 6 equal sides to a dice, so there are 6 equal likely outcomes, the theoretical probability for each outcome will be 1 out of 6. So I have 2 colored dice here, right? I have one with 6 sides, I have another one. So when I roll that, getting a 2, that is 1 possibility out of 6. There's 6 sides, right? On this one, oh, I wrote a 2 again. So if I got a 4, the chance of getting a 4 is still 1 out of 6 because there are 6 sides and getting one of them is 1 out of 6. So it's the number of ways A can occur out of the total number of outcomes. A 4 can occur 1 time out of the total possibility of 6. All right, counting outcomes. Suppose we toss 2 coins and want to count the total number of outcomes. The total outcomes for the first coin can each occur with either of the 2 outcomes for the second coin, making a total of 2 times 2, because there's 2 possible outcomes times 2 possible outcomes gets you 4. Now, if we flip the 2 coins, first of all, we're going to get heads or tails. And then that head, when we flip that coin, we get a possibility of heads and tails. And when we flip the tail, we get a possibility of head and tail. These are the 4 possible outcomes that we get. We can get head, 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 tail, tail, head, tail, tail. All right. So, if we observe that it rains an average of 100 days per year, we might say that the probability of rain on a randomly selected day is 100 out of 365. Because if they're saying that it rains an average of 100 days, that's the number of times it occurs out of the total number of days of observation, which would be 365 days in a year. For subjective probabilities, where we're at in our video. Make sure that you saw everything I was talking about. If you're in my class, you have the handout. It's in your D2L. Just go pull it up. All right, so subjective probabilities. For example, you could make a subjective estimate of the probability that a friend will be married in the next year, or of the probability that a good grade in statistics will help you get the job you want. So it's kind of an intuition, opinion kind of thing, right? So the probability of an event not occurring, that's going to be called the complement, is that A does not occur, or P not, the probability of not A, remember all the probabilities equal to 1 for an event. So you take the 1 and you subtract out the probability of A occurring. So that's the basic information you need to know. Let's go work some problems. So for example 1, family outcomes and events. So part A, consider families with 2 children. List all the possible outcomes for the birth order of boys and girls. If we are only interested in the total number of boys and girls, the total number of boys in the families, what are the possible events? So we're interested in the total number of boys, but we're going to list the total possible here. All right, so this will be example 1. So for example 1, part A, and this is 6.2, if we want to list the possible birth outcomes, it's very similar to flipping the coins, because for each child that is born, there's a possibility of a boy and a possibility of a girl. So I'm just like, there's a blue and a red, right? So a boy and a girl. So there's 2 possible outcomes. So when somebody has 2 children, they could have had 2 boys. They could have had a boy and then a girl. They could have had a girl and then a boy, or they could have had 2 girls. So this probability of having a boy or a girl is going to be the same as flipping coins, because there's 2 possible outcomes. So the chances of having one is going to be 1 out of 2 for each one. Now, they really wanted to consider what's the total number of boys that they possibly could have. Well, we could have 0 boys. Now, let's go backwards. We have 2 boys for this one, right? And then we have a boy, girl, and a girl, boy. In those both cases, we had 1 boy. And in this last case, down here, we had the probability is having no boys, right? So 0 boys. So the possible events will be 2 boys, 1 boy, or 0 boys. All right. So those are the possible events. These are the possible outcomes. So let's make a note. This is the outcomes. These are the events that can occur. All right. So that's the possible. We were asked to find the possible outcomes, and then what are the possible events. All right. So let's go and do part B. So for part B, what is the probability of rolling 2 ones, snake eyes, when 2 fair dice are rolled? All right. Hang on 1 second. Okay. So if we're looking at the possibility of rolling 2, oh, that's why I'm like, what happened? I skipped a problem. We're not on 2. We'll get to the snake eyes here in a minute. I'm like, those don't match my notes. What is the probability that a randomly selected family with 3 children has 2 girls and 1 boy? Assume that the birth of boys and girls are equally likely. So, in this case, they have 3 children. What is the probability you get 2 girls and a boy? All right. So, we're going to list the possibilities. First of all, let's look at how many total possible outcomes are there, because that's always a helpful thing. So for having a child or rolling or flipping a coin, it's the same, right? There are 2 possible outcomes. So for anything that has 2 possible outcomes, there are 2. And then for having another baby, there's 2. And for a third baby, there's 2. To find the total possible, we're going to multiply that. Earlier we flipped coins and found that 2 times 2 got us 4. In this case, 2 times 2 times 2 will get us 8 possible outcomes. Knowing that will help you know, like, what are all the possible outcomes that could occur. All right, so let's go make a list. So we could have all boys. We could have 2 boys and a girl. We could have a boy, then a girl, then a boy. We could have a girl and then 2 boys. We could have a girl, then a boy, then a girl. We could have 2 girls and a boy, or we can have 3 girls. So 1, 2, 3, 4, 5, 6, 7. All right, we're missing one, so let's go back and look. We have 3 boys, 2 boys and a girl, a boy, a girl, a boy. Let's see. Oh, so three boys, 2 boys and a girl, 2 boys, a girl, a boy, and boy. So I've moved. The one I'm doing here is I did all of the boys. I did 2 boys and a girl, and then I moved the G over one place. I moved it over one place, and then I moved it over another place. So that makes sure I don't miss one. Over here, I did a girl, a boy, and a girl. I did a girl, and a boy. I did not do a boy, a girl, and a girl. So I missed this one here. A boy and 2 girls. Okay? I try to do it in an orderly fashion. So I might have started instead of going to here, but because I have the girl, I went, oh, well, let's just switch. So I moved, I put a second girl in, I moved her over, but I didn't move them all to this way so that the boy was at the front. All right, and then so you have all of the boys and all the girls. So there's 8 outcomes. And again, by figuring out that total possible, I'm like, okay, I know I'm missing one. Now, the question talked about having 2 girls and 1 boy. So, where did we have 2 girls and 1 boy? Well, we have 2 girls and a boy here, 2 girls and a boy here, and 2 girls and a boy there. So that is the probability, I'm going to write this out a little bit, of 2 girls. And we don't even have to put the 1 boy, because if we have 3 kids, we know it's 2 girls and 1 boy, right? So the probability of having those 2 girls would be the outcomes with 2 girls out of the total possible outcomes, which is 8. And then we can change that. The fraction won't reduce. We could change it to a decimal, and again, 3 significant values there. Alrighty, so that is example 1. Let's go on to example 2. So 2 dice. How many outcomes are there if you roll 2 fair dice? Alright, so how many sides were on our dice? There are 6, right? I have 6 on this one, and I have 6 on that dice. So the total possible outcomes, it's going to be very similar to what we just did. There are 6 on one dice times 6 on the other. There are 36 different possible outcomes when you roll 2 fair dice. And they're going to use the word fair a lot because they want to make sure it's not a trick dice. That means that when they say fair, it's equally likely to have occurred. All right, what is the probability of rolling 2 ones to get snake eyes, right? So they want to know what is the probability that when we roll this, we get 2 ones. So, well, there's one possibility of getting 2 ones out of the total of 36. So for part B, the probability of getting 2 ones is going to be the number of ways that it can occur. Now, we talked earlier about when we were flipping the coins, right? We talked about this. Let me just do the dice because they're easier to see. If I roll a 1 and a 2, this is not snake eyes, this is just a clarification. If I roll a 1 and a 2, and then I roll a 2, got to do it on the right color, sorry. Got to find the 2, and the 1. 1 on the blue and 2 on the red is not the same roll as a 2 on the blue and a 1 on the red. This is just like the dice, the coins. A head and a tail versus a tail and a head. It's different outcomes. So these get counted as different outcomes, okay? But when we roll snake eyes, like 2 1s or 2 4s or 2 5s or 2 6s, these are only counted as one outcome, just like 2 heads is one outcome versus 2 tails. When we did the heads and tails, we did not move and say, well, with this coin, it's this, and with this coin, the heads and the tails part, I don't look at, okay, I've got 2 heads here, or 0 heads. If I have 2 heads, well, I get 2 heads 2 ways, because then I'm going to move the coins around. It doesn't work that way. You get 2 heads, that counts as one occurrence. And just like no heads, where you get 2 tails, it happens once, all right? So same thing happens here. If I get the same number on the dice, that's just what it is. It won't happen twice. Like, well, what if we move it around? Nope. In these cases, it is the exact same. The difference is if you don't get the same number, these are considered 2 separate events. So that's a really clear clarification for you. So getting 2 1s will only occur one time. Our total is out of 36. And if we turn that into a decimal, it'll be 0.0278, 3 significant digits after the 0. All right? Okay, so the next problem that we're looking at is example 3. There are 52 playing cards in a standard deck. So this is stuff you've got to know, just so you know. There are 4 suits. There's hearts, spades, diamonds, and clubs. I've got a little bit of a picture down here for you. Each suit has cards for the numbers 2 through 10, plus a jack, queen, king, and an ace, for a total of 13 cards in each suit. Hearts and diamonds are red, spades and clubs are black. We want to know, if you draw 1 card from a standard deck, what is the probability that it is a spade? All right, so let's pull some actual cards in. So this is a heart, and this is what we call an ace, because I know not everybody, when I was growing up, everybody played with cards. And I even played cards with my kids. But in today's world, everybody doesn't know what a deck of cards is, and they don't know how to play with a deck of cards. So I'm going to go over this. So if you know this is great, and if you don't, this is something you need to know. This is what a queen looks like. You don't need to know what a queen looks like. You just need to know it's going to have the Q on. These are called face cards because they have a face on them. So here's the Jack of Clubs. He's a face card because he has a face on him. So the queen has a Q, the Jack has a J, and a king will have a K. And I know there's a king right here, so let me pull him out. The King of Spades, he's also a face card, and he's got a K on him. So these are your 3 face cards. Now there's also going to be number cards. There's like a 9. This is a spade. And there's a 4 of clubs. Here's a 3 of diamonds. Here is a 5 of hearts. So those are what we call the number cards because they have a number on them. What I want you to make sure you know is that in a deck of cards, there are the number cards that are 2 through 10. So 2 through 10 on the number cards. There's an ace, and then there's a jack, a queen, and a king. And they would go in order this way. These are different suits, but that's kind of the order they go in. All right, now, what you really need to understand is their hearts and diamonds are red, and clubs, they kind of look like a clover, and spades are black. Now, in my house, these were hearts and diamonds. Those are easy. My kids called these puppy toes because they look like a little puppy paw print, and these were called shovels. So, spades and clubs, diamonds and hearts, red ones and black ones. There are 52 cards in a deck. So I'm going to write a couple of things down for you. And it states that in there, but I want to write because this is important for you to know. This is something that you would need to know when you take the exam, so make sure you're learning this. So we're just going to look at cards for a minute. There are 52 cards in the deck. There are 4 suits, and there are 13 cards in each suit. So you need to know that those suits are hearts, diamonds, clubs, and spades. That's all listed in your handout. And what if you get on the test and you're like, man, I don't remember how many cards are in each suit? Well, if there's 52 cards, and you can remember there's 4 suits, if I divide 52 by 4, I get 13. So you can figure it out mathematically how many were in each suit, okay? And there's going to be the Jack, the Queen, and the King as far as face cards per suit. The other thing that you should note, let me see if I can find that real quick. So I have, looks like queens are popping up here. When you're looking at, like, what's the probability of drawing something? If we're looking at drawing the probability of drawing a queen out of the deck, there are 4 queens because there's 1 queen in each suit. That would happen the same way for 4s, for 9s, for aces, for kings. There's 4 of each card in there, 1 of each suit. So that's something else that you're going to need to understand. All right, so let's go look at our question. So this will be example 3. The question was, if you draw 1 card from a standard deck, what's the probability that it's a spade? Well, the probability of drawing a spade is going to be the possible outcomes again. What's the total possible outcomes? Well, there's 13 cards in each suit, so there are 13 spades in the deck out of a total of 52 cards in the deck. So the possibles out of the total, and that's going to reduce down. 13 divides evenly into 52. They both reduce by 13. It's going to be 1 out of 4. Because 13 divided by 13 is 1. 52 divided by 13 is 4. So it'll be 1/4. And then you could change that into a decimal. But on some of these, it's just going to be good to leave them as a fraction. All right. So understand this stuff. You'll have some homework in this, and you'll also have an activity at the end of chapter 6 that'll work on and help you understand these concepts. And we've got some more examples coming. All right, so the geological records indicate that a river has crested above a particular high flood level 4 times in the past 2,000 years. What is the relative frequency probability that the river will crest above the high flood level next year? All right, so we're looking for the probability that it's going to flood, right? Or have a high flood. So this will be example 4. So that probability of a high flood in this one, because it's a little bit different, we're going to look at the number of years with a flood out of the total number of years. So, what were the number of years we had a flood? Well, it was 4 out of the total number of years is out of 2,000, and that's going to reduce down to 1 out of 500. And that's why it's called a 500-year flood, because about once out of every 500 years, it's going to flood. So, all of these are about the total number of the event occurring out of the total number of possibilities or observations that you looked at. Okay? All right. So you don't expect it, just to be clear, you wouldn't expect it exactly every 500 years to occur. It just means that it has a 1 out of 500 chance of occurring in any year. And typically it's not going to it could happen sooner, and then it could be a longer time, but on average it's going to be about 1 out of 500. All right, let's go to example 5. So example 5 says to identify the method that resulted in the following statements. I'm certain that you'll be happy with your new car. So we're looking at the type of probabilities. So remember, we had 3 types. We had theoretical, we had, here we go, theoretical, relative frequency, and subjective. So theoretical was we do some kind of equal outcome, equally likely outcomes, and the number of ways of an event occurred by the total possible, your relative frequency, based on the observations or experiments. And then subjective is an estimate based on experience or intuition. All right, so let's go look at these again. So identify the method that resulted in the following statements. I'm certain you'll be happy with your new car. Well, that's not an experiment, and that's not a bunch of observations so much with relatives. It's not the number of times it occurred. It's more of like, it's an opinion of the speaker, right? Oh, it's probably a car dealer, or it's their friend, or whatever. So for example 5, part A, this is going to be a subjective, because it is an opinion. I'm just going to put opinion. Whoops, sorry, you can't see. Happens in class too. Because I teach on the document camera just like this in the classroom. Makes it easier for everybody to see. All right, part B, let's go look at this one. Based on housing data, the chance that someone will move to a new residence during the coming year is about 1 in 8. Well, that looks like they've got some information going on there. We've got some data that shows that about 1 out of 8 of the population moves to their residence during a given year. So that's probably looking at the number of times it occurred out of the total number of observations. So this one's going to be a relative frequency. And that's because we're looking at some data with the some calculations, right? So we've got the number of times occurred out of the total number of observations that have happened. We haven't done an experiment. These are observations, right? So this one is number of occurrences out of the number of observations. Because people moving is an observation, it's not an experiment. All right, and then C talks about the chance of rolling a 7 with a 12-sided die is 1 out of 12. Well, why is that 1 out of 12? Well, if there's 12 sides, that means you have 1 through 12, and there are different dice. I showed you a standard dice. Sorry, that's probably a little noisy on the video. But there are other types of dice. So let's pull a couple of these out so you can see. Plastic bags are great. Sorry, it is so noisy. So sorry. I just want to pull out some different ones. So like 2, 4, 5. There are different dice here. So they go to different totals. I think this one's a 30-sided dice. because there's the high number of 30. And this one is also a 30-sided. It's just a different color. I see a 19 on this one. This one's a 20-sided dice. And this one is a 12-sided right there. And this one, it looks like it's a 10-sided dice. It has a side of 0, and it goes up to 9. So this is a 10-sided dice. So these are used in different games and whatever. But so if we're looking at a 12-sided dice, rolling a 7, there's only one chance of rolling it out of all of the 12 sides. So it's going to be 1 out of 12. Now, what does that show us? If we're rolling a dice, that's a type of experiment, right? So the type of probability for this one is going to be a theoretical. Theoretical probability. So the theoretical probability is where we have the number of ways it can occur out of the total outcomes. So number of ways it can occur over the number of outcomes. And up here, I need to clarify, this is the number of times. So number of times it occurs, or occurrences, and this is the number of ways it can occur. So a little bit difference in the wording. So that's theoretical. So I wanted you to understand the different ways. All right, let's go find some probabilities. To find the probability of the event, not drawing a queen from a standard deck of 52 cards. Now I had the queens out a minute ago, right? How many queens are there? Well, there's 4 queens in the deck. And if you recall, we talked about the probability of something not occurring will be the total possible is 1 minus the event. So not drawing a queen. So part A would be the probability of not a queen will be equal to 1 minus the probability of drawing a queen. So this will be equal to 1 minus the probability of getting a queen. There are 4 queens out of a total of 52 cards. So I need to make a common denominator here. 52 over 52 minus 4 out of 52. That'll get us 48 out of 52, because once we get a common denominator, and that's just changing your 1 to the same denominator, right? 52 minus 4 is 48. Our denominator stays the same. These are both divisible by 4. If you don't know that, you can, they're both even, reduce by 2, and then reduce by 2 again. 48 divided by 4 will get us 12, and 52 divided by 4 is 13. So 12 out of 13. All right, and this is good math for you to be able to do. There's not a lot of math in this course so far. You've probably noticed. There is a little bit, but not a ton of math. All right, our next question is randomly selecting a day of the week and not picking a day whose name includes the letter T. So how many total days of the week are there? Well, there's Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? There's 7 days, so that's our total on the bottom. Now, how many have whose name includes the letter T? So we've got Sunday, Monday, Tuesday has a T, Wednesday, Thursday has a T, Friday, Saturday. There's 3 of them that have a T. Tuesday, Thursday, and Saturday. But Monday, Wednesday, Friday, and Sunday do not. So for this one, this will be part B. We're having the probability of not a T in the name. This will be equal to 1 minus the probability of having a T. So this will be 1 minus 3 out of 7, because there were 3 days of the week that had a T out of 7 total. This will get us 7 over 7 minus 3 over 7, and that'll get us 4 out of 7. All right, and number 7. Does it make sense? When randomly selecting a month, the probability of selecting a month with 32 or more days is 0. So when randomly selecting a month, the probability of selecting a month with 32 or more days is 0. Well, does that make sense? So how many days are typically in a month? Well, February has 28, unless it's a leap year, it's 29. There are several months that have 30. There are several that have 31, but none of them have 32. So the probability of selecting a month with 32 or more days is true. It's going to be 0. There are no months with 32. So for example 7, it's going to make sense. And because there are no months with more than 31 days. So the chance of selecting one at random is going to be 0. All right, so do your homework. And if you're getting stuck on anything, let me know.